Hi, my name is Katie Breivik. I am currently transitioning between postdocs at the Canadian Institute for Theoretical Astrophysics and the Flatiron Institute's Center for Computational Astrophysics. Today I'd like to talk to you about some work that was recently accepted in AppJ that I've been doing with Chiara Mingarelli and Larson on constraining the galactic structure with the Lisa white dwarf foreground. Now, when most people think about constraining galactic structure, Gaia immediately comes to mind, and that's because Gaia's precision measurement of positions and velocities of some billion stars in our galaxy give a fantastic measure of the galactic structure. It's illustrated here by the yellow swaths, which are showing Gaia's reach for main sequence stars, and the purple swaths, which are showing Gaia's reach for giant stars. And it basically reaches all across the galaxy. So Gaia's galactic structure measurements for living stars is really unparalleled. However, if you're interested in white dwarfs and the structure of the galactic white dwarf population, Gaia is really not going to help you, and that's just because its reach for white dwarfs is limited to roughly 300 parsecs. That means that Gaia is not going to help us here, but of course, this is for the virtual LISA symposium, so I'm not going to keep talking about Gaia. Let's think about what LISA can do with the white dwarf population. So LISA can observe a resolved double white dwarf at 2 millihertz in gravitational wave frequency, basically to the same reach that Gaia can see for giant stars. That means that what Gaia gives us for living stars, LISA can give us for the galactic double white dwarfs. So to investigate what this actually looks like and see how well LISA can constrain the double white dwarf population, the first thing that we did was, of course, simulate a double white dwarf population. We did that using the population synthesis code that I lead the development of, COSMIC, which stands for Compact Object Synthesis and Monte Carlo Investigation Code. Some features of this are that, first, we are based on fully open source stellar evolution grids from BSE. We quantify the convergence of binary parameter distributions, so instead of just picking a number of binaries to evolve, we actually use the binary evolution models themselves to determine how many systems we need. It's also fully open source developed in Python, which means that you can pip install Cosmic PopSynth and use it right out of the box. And it is also fully documented. So if you're interested, I would really encourage you to check out our documentation at cosmicpopsynth.github.io or our code paper that I put in a bunch of work with Scotty Katelyn and Mike Zevin on over the past year. So we took simulated double white dwarfs from our population and we distributed them into a galactic model from Paul McMillan's paper in 2011. And this model has three components. The first one is a thin disk, which distributes the double white dwarfs with a radial exponential falloff and a vertical exponential falloff with these two scale heights, ZH and RH. There's also an axisymmetric bulge, as well as a thick disk. And the difference between the thick disk and the thin disk really is only in their scale heights. Okay, so if you take the double white dwarfs and this galactic model, this is what the Lisa white dwarf foreground looks like in the amplitude spectral density. And this is taken directly, this population is taken directly from our Cosmic PopSynth paper, and that is all open source and you can actually access all of that data today. Now, we're in the business of actually trying to constrain galactic structure, so we took this simulated population and we compared it with a different population to ask, can LISA infer the vertical disk scale height of the Milky Way's double white dwarfs? We have two models. Z300 is the standard model where we have a thin disk with 300 parsec vertical scale height. And we also have Z900 where we have a vertically heated thin disk that actually has the same scale height as our standard thick disk. The reason that we choose these models is because this is about as extreme as you might guess that the double white dwarfs could be vertically heated. And they could be vertically heated for a number of reasons. They could be from large-scale dynamical interactions or interactions with dark matter clumps, different things like that. But these two models sort of encompass the farthest extremes that you might expect the double white dwarf population to be heated. And what you can see here is that if you're only studying the amplitude spectral density and nothing else, it's really difficult to tell these models apart. There are some things that you can infer, namely, if you vertically heat your double white dwarfs, the amplitude spectral density falls by some amount, but this is well within the uncertainties of our binary evolution models, so that's really not going to help us so much. However, if you distribute these populations, again, sorry, we are looking to compare these specific vertical scale heights. If you compare these populations in two-dimensional space, just their projection on the sky, it's very clear that the 2D projection of the amplitude spectral density is very different. And so for this study, instead of studying the resolved double white dwarfs, as had been done in other studies, we take this 2D distribution and we consider the angular power of the double white dwarf foreground altogether on the sky. So we can do that. We follow the exact same parameters as is done in cosmic microwave background to make an angular power spectrum of the double white dwarfs. And this is really simply done using the standard spherical harmonic decomposition, where we distribute the power on the sky using spherical harmonics, and then we calculate the angular power spectrum. And you can see that there is a difference between the angular power spectra of our two models. However, the difference is not really, the measurable difference isn't really illustrated here, and that's what I'll be talking about for the rest of this talk. In particular, you'll note that the multipole moments that we are showing here is only up to 12, which is honestly tiny compared to what you would see on a cosmic microwave background plot where L goes all the way up to 200 or so. So the question now is the angular power spectrum enough? And to do that, we need to think about LISA's angular resolution. So LISA is measuring different data streams, different correlated data streams as shown here, where you have different correlated channels. So this C tilde is the Fourier component of different correlated channels ij, and S sub h is our signal from our white dwarf foreground, and then Fij is LISA's response. And all of the work that I'll be talking about here, we followed very carefully with Kudo and Tarubia here. So I would definitely refer you to that paper to see all of the details. So we have our Fourier component of our correlated signal, Cij, and we use the simulated double white dwarfs to make this signal. And then we can take LISA's response, this Fij here, where we transform the LISA response function into the plane of the sky, because LISA is, of course, cartwheeling around. When you do that, you can see LISA's response, and it turns out LISA's response is actually not super great. Unfortunately, LISA doesn't have a really fantastic spatial resolution, especially down at the millihertz regime, which is what we are considering because we're looking at the double white dwarf foreground. So when you're considering this, we take advantage of the fact that LISA's motion is periodic. So we take the Fourier component of the correlation and we Fourier transform that again on LISA's yearly motion. And this allows us to actually write down a function to solve for these multipole moment PLMs of the double white dwarfs on the sky. When you do that, you can actually calculate what the signal to noise is for this Fourier transform of the Fourier component of LISA's correlated data streams, and that's what you see here. We compare specifically the A, E, and T data streams because these are the optimal data streams that were solved for back in the early 2000s. And you can see that the data streams that we really care about are the AA and EE, and these are pretty much equivalent, and then there's the AE cross-correlated data stream. And it's this set of data, these set of C sub k's, where k can go from -4 to +4 for each of our correlated data streams, that we'll be able to build a map of the PLMs. In particular, it's important to note that with these data alone, LISA is only sensitive up to an L equals 4. So the angular power spectrum isn't going to tell us too much, but the PLMs we can actually solve for. And when you go through and actually solve for this, you can see that for the n equals 3 and 4 multipole moments, LISA can actually distinguish between these two models, the Z300 and Z900. So that means that LISA does have some resolving power to tell whether or not the double white dwarfs are all in a vertically heated population or not. Now, of course, these are two extreme models. We decided to look at a varying scale height. So we cranked our models from 300 to 900 scale height parsecs. That was, of course, the difference between our two extreme models to see how well we could distinguish between different vertically heated scale heights. And what I'm showing here are each of these multipole moments, the m equals 4 and m equals 3 multipole moments, and showing you where LISA's observed distributions are distinguished. So everything that is a cross is what LISA would see if the double white dwarfs are not vertically heated, and the blue is what LISA would measure if they are. LISA is able to distinguish all systems that are in the green shaded region. So it's roughly it's roughly in the area of if the double white dwarfs are distributed between 600 or 650 vertical scale heights. So that's a difference between something like 300 to 350 parsecs. We actually then did this same experiment 1,000 times to just ask, okay, at what scale height is LISA able to distinguish one of these multipole moments? And it depends on how comfortable you are with how lucky we might be with the galaxy, but we think that a good estimate is if more than half of the realizations are distinguishable with a given scale height, then we'll take it. So it's basically between 250 parsec resolution to 300 parsec resolution. So how does that compare to other ways of measuring galactic structure? So Valeria Corral has a really fantastic paper showing how LISA can measure the galactic structure from resolved double white dwarfs, and this measurement resolution is roughly 50 parsecs or so. And of course then there's Gaia, which is observing the bright stars, and that resolution is really just unparalleled at 5 to 10 parsecs. So our 250 to 300 parsec resolution isn't great compared to the others. However, there are some strengths here, and in particular, being able to independently measure the galactic structure of double white dwarfs from both the resolved and unresolved foreground is a very powerful measurement. So what's next for these types of studies? First, it would be really interesting to see what the variance is between different binary evolution models and how those would affect this type of measurement. It's also interesting to consider other types of galactic components. In particular, it would be really fantastic to see if the double white dwarfs are distributed in a bar. It would also be really nice to see if galactic sources like neutron star or black hole binaries cause biases in our foreground. We really only considered the double white dwarfs. And it would be really interesting to see if this type of technique is a better way to subtract the galaxy's foreground for other cosmological stochastic backgrounds. And with that, I will leave you. Thanks so much for listening and enjoy the rest of the symposium.